This is lecture 4 where we'll be looking at three different interpolation techniques. So these techniques are basically the Newton's divided difference polynomial, Lagrange polynomial, and Neville's algorithm. The first two interpolation techniques are based on a polynomial fit. So before I begin, what exactly is an interpolation? So I'll give you an example. In engineering, we often face a lot of data in discrete form, and these data are basically obtained from your measurements. So let's say you have a series of data points that list out your temperature versus time. So at different points of time, you are recording the temperature of, let's say, the machine that you're running, or the heating of a plate, and so on. So the question now comes to this. You have time at every interval of 5 seconds. Say for whatever reason you're interested to know the temperature at 7.5 seconds. How can you recover, or how can you estimate the temperature at 7.5 seconds using the data that you have over here? In fact, you guys would have dealt with interpolation when you were doing your thermodynamics. Remember when you're given the steam table and you're supposed to find the properties of water at a given temperature, but that temperature is not given to you in the steam table, you do a simple linear interpolation. So that itself is an interpolation. So by definition, interpolation is basically to use a limited number of function values to predict the value of a function at other points within the range of your data. Now I've underlined this phrase here, within the range of data, because that definition is important to what, or to how we define interpolation. Let's say you're given this set of data points here. You have 0.1, 0.2, 0.3, 0.4, 0.5. You have 5 data points, and the blue line represents your actual curve. Now the range of data points that we refer to here refers to these 5 points that we have. So this is your range of data points, and when we say we are using the range of data points to predict the value of a function, it means that suppose that we are interested to find out what is the value of y at xp here. So our xp is within the range of our data points, so in doing so we are actually performing an interpolation. But sometimes we may have to find out the value of y when xp is beyond your data range. So you can see xp right now is beyond the largest value for x5. So we are saying what we can say from here is that xp is beyond the range of data that we have. In this case, what we are doing is we are doing an extrapolation, just because the point that we are interested in lies beyond the range of data points that we have. So you should be able to differentiate between extrapolation and interpolation. Extrapolation is not accurate. For example, like I said earlier, this blue curve here probably represents the actual line, but we only know up to the fifth point over here. Whatever happens after this is beyond what we know. So if you fit a curve to this, we might probably extend this curve downwards, but in reality your curve could have gone up, but we wouldn't know because the only data points that we have are from 0.1 to 0.5. So if you carry out your extrapolation, you can see that the error that you get here is going to be large. That is because when we do extrapolation, in a way we are trying to use the points that we have to estimate what goes on beyond the points. That is similar to stock market prediction. You're using all the data from your history of how the stock market behave to try to predict what goes on in the future. So it's more prone to error. That is why we try to avoid having to do extrapolation in engineering. Not to say that we don't do it, but it's you should know that it is actually more prone to error than interpolation. Now, in the MATLAB software that you're using for this unit, there are a few inbuilt functions that help you to carry out interpolation. So all of these have been covered in engineering ENG 1060, so I'm not going to repeat them. But the two functions that you have are basically polyfit and polyval. So these functions are basically based on a least square approach, and it is not similar to the ones that we are going to cover in this lecture today. Now, when we do interpolation, there are basically two steps that are involved. The first step involves your curve fitting process. So the curve fitting process is basically fitting a curve through a series of data points that are given to you. Once you have obtained this curve, you will be able to get the equation that describes this curve. The next step would be to use this curve to estimate the value that you want. So you'll be using the fitted function that you have, and you're going to use that function to predict the value of y at a given point x. So when we talk about interpolation, there are actually two types of interpolation. You have global interpolation and you have local interpolation. Global interpolation uses all data points that you have to find the estimate at a single point, and these will be the Newton's divided difference polynomial and Lagrange polynomial that we'll cover later on. And you also have local interpolation that uses only data within the point that you're interested in. So it can be two points, it can be 3 points, and so on. But you do not use the entire range of data. You only use certain points of certain amount of data that you have that is in the close vicinity of the point that you want to interpolate. Alright, so I'll just give you a simple example on what I mean by the two steps of interpolation. So let's say you have 3 data points here. You have 3 values of x and 3 corresponding values of y. And what you're interested in is you're interested to use a quadratic function to fit these 3 points over here. Okay, so we know that the quadratic equation is given by yx is equals to ax squared plus bx plus c. This is straightforward. So in order for us to fit a quadratic function given the 3 points that we have, what we are going to do is we're going to substitute the value of x and y into our equation. So for the first value of x, we have 1.5. For the second value of y, first value of y, we have 0.75. So if we substitute this into our quadratic equation, we are going to get 0.75 is equals to a, because a, b, and c are unknown coefficients that you're supposed to find. So this will give us 1.5 squared plus b, 1.5 plus c. This is our first equation. Now we're going to repeat the same thing for the 2 other points. So for the second point, we have y is 1.2 is equals to a 2.25 squared plus b 2.25 plus c. So this is our second equation. And in the third equation, we have y 0.6, and we are going to repeat the same thing. So we have your third equation over here. So theoretically, having 3 equations and having 3 unknowns, what are our 3 unknowns? A, b, and c. Having 3 equations and 3 unknowns, we should be able to solve this as a system of linear equations. So this can be done by either solving this directly using Gauss elimination or any of the techniques that you have learned from lecture 3. So if you solve this, you'll find that the values of a, b, and c are given by this. So once you go back to your quadratic equation, which is your ax squared plus bx plus c, you get your following function or your quadratic fit here. So let's suppose that you're interested to find out the value of y at x equals to 2. You can then use this quadratic fit to find out what is the value of y at x equals to 2. So if you calculate this, you'll find that this is equals to 1.1688. So this is the idea of interpolation. Whatever we do to find the coefficients a, b, and c are basically fitting the curve through the data points that we have. Once we have the curve, we use the curve to estimate the value at the point that we are interested in. Now, this example or the simple example that I've shown to you is only for 3 points, but you can easily extend this to more data points that you have. So if you have 4 points, you have a cubic polynomial. If you have 5 points, you would have a 4th order polynomial, and so on. The only downside of this is the coefficients that you have or the number of unknowns that you have would increase with the number of data points, which means that if you have 10 data points, you would have 9 order polynomial. If you have 9 order polynomial, you need to inverse a 9 by 9 matrix. Alright, so that is one limitation. The other limitation is that this method cannot be generalized to any given data points. So what this means is you cannot write a code based on this method here and then try to use that code to solve any set of general data points. Reason being, this method cannot be generalized. So this is it for this part of the lecture. In the next part, we will be looking at the Newton's divided difference polynomial, which will allow us to generalize the method to find or to carry out interpolation.